Hi, good evening, and welcome to the ZP Developer Zone. So every week we like to do a ZP Developer Zone where we answer technical questions from the week. I was intending to do this on the 30th of June, and I always actually like to do this live, but more and more I'm actually finding that my broadband is slowing up. So I think it's time for me to go to fibre. That said, it's the 29th of June 2024. I've had to record this, and I'm going to not speak too fast, but I am going to go through quite quickly. There's plenty of, as per normal with ZP, plenty of content. So I'm going to talk about geosmin. Geosmin is something I've been aware of sort of pre 2019. There's a lot of things going on in, for example, Norway called RAS farming, recirculating aquatic systems, where they're basically growing the salmon in a recirculating tank on the land. And one of the things they want to avoid is geosmin, because if you get bacteria in there and the bacteria produces geosmin, then the geosmin gets into the flesh of the salmon and you end up with a not very, I think it may have a smell, a bit of a smell and a bit of a taste, and it puts off the consumer. So I will talk about geosmin. I will also talk about sweat analysis. This particular person is interested in potassium, sodium, chloride, and also the rate of sweat analysis. Now, doing the rate of sweat analysis is something that ZP will do as a program, but programs with ZP can be, very large, multi-$100,000 style programs. So if people are really got sort of smaller budgets, etc., then I can only talk really about sodium and potassium, and a little bit on chloride today. But what I talk about is the things I'm recommending to you. But if you need deep questions with Zimmer and Pico, and this is all new to you, then unfortunately those are called, those will be programs, and we'll charge for programs. But if you're able to follow along what I'm able to say today, or what I am saying today, then hopefully you can buy the web store stuff and do some proof of principles with that. So I will talk about this sweat patch and measuring. I'll be directing more towards potassium and sodium. We've got some upcoming webinars at ZP, so something I'm quite particularly passionate about, and it will be relevant to the geosmin. In front of me today, I've got one of our Sense All. I'm starting to call it the Sense All Potentiostat. When we first came out with this, we were not intending to necessarily make it a potentiostat. Now this QR code will appear shortly, but if you're interested in doing, for example, geosmin testing, and you've got an Android, then this QR code, which will appear in a bit, will be interesting. If you've got an iPhone, this QR code will be interesting. And as I say, we're starting to kind of call it a potentiostat. I originally didn't intend it to be a potentiostat, but I got some QR codes here. These QR codes will also come up in this webinar today. And the top row of QR codes is all about analytes. We've got a system where actually we are able to create assays, so we've got like amperometry, open circuit potential, EIS, linear sweep voltammetry, cycle voltammetry, square wave voltammetry. So these are standard classical electrochemical assays. We're actually able to then turn them into, let's say, analyte specific assays. I've got total antioxidative capacity here, glucose, chili, ginger, potassium, pH, nitrate. These are just something that we have done, but the entire platform is actually designed to get technology out of the lab. I think one of the first paragraphs we wrote on the ZP website 10 years ago really was, ZP is part of the Internet of Things revolution, and we see there's a large sort of mine of great science going on in labs, but it never really comes to market. So that's something that we're trying to fix, and we're trying to fix it through this platform. And I think the geosmin conversation today will sort of highlight how we see this actually coming in. If you're interested in Sense It All, there's a webinar on the 11th of July. We do one in the morning, one in the afternoon. ZP, I happen to be located in London, UK, which is great because actually if I do a webinar in my morning, then I can hit Asia. And if I do a webinar in my afternoon on the same day, then we hit, let's say, North America, South America, Central America. So that's why we do two webinars on the same day, because then we essentially cover the globe. If you see a URL jump up, then I'll put those underneath the webinar. We are also doing wearables. Now, I appreciate the person today is asking about sweat analysis. I'm not going to super talk about it now, but just understand that there is a webinar on wearables, and I'll probably talk more about microneedles, this technology here for measuring glucose, lactate, or ketones in what's called the interstitial fluid. That's had 20 million euros spent on it. So you've got to be careful with wearables because wearables, I would say, is at least 10 times harder than doing what I call in vitro diagnostics, which is the technology that I have here. But that said, if you're interested in wearables, then we've got webinars on the 9th of July. It's probably worth saying that even if you're watching this after 9th of July, the links underneath this video, we keep updating the page when the next webinar will be on. So the links will remain relevant. And we are doing a webinar for academia on the 18th of July. Interesting, actually. Yeah, we're doing one for academia on the 18th of July, one in the morning, one in the afternoon. Same idea. By doing one in the morning, one in the afternoon, we actually cover the globe quite nicely. And question number 1, geosmin. So I got sent a paper on geosmin. Here they're doing, they're using a FET, and they're using a graphene FET, a field effect transistor. And FET, as you all probably already know, has a drain and a source, or sorry, I should say a source and a drain, really. And between it, then they have this kind of graphene sheet. And they're controlling the sort of voltage at that graphene sheet and using what we call a gate. They have a sort of third gate voltage in their circuit as well. But you'll see that as I go through here. They've functionalized the graphene to be functional towards or specific towards geosmin. I'm not super sure it's going to be that specific towards geosmin. Geosmin is not a very functional molecule. And what I mean by that, it doesn't have aromatic rings, it doesn't have amines, it doesn't have carboxylic acids, it does not have a lot going on with it. It just has carbon, hydrogen, and not even that many double bonds on it. So quite hard to make it specific, but you know, we take the paper as written. I'm just doubtful it's actually as specific as they would otherwise like. But we'll go through that now. So this is what I use the images straight from the paper. This is only because I'm essentially reviewing the paper. So they've got their and of course you can download the paper off the publisher's website or get it from ResearchGate, I suspect. So there's a drain and a source on this, and they've put an aptamer between the drain and the source on the graphene, and the aptamer is meant to bind with the geosmin and give you a signal. I'm sure it does bind with the geosmin. I'm just sort of suspicious that it's not quite as specific as they would like. And now one of the things at Zimmer Peacock is, I did say, we're quite keen on getting science out of the lab. So I try to remove as many barriers as I can between doing something in the lab and doing something that's actually kind of impactful and can get out of the lab. So it's not a criticism of the paper, but the first thing they do is they describe quite a procedure for making the GFET. Now, I know that there are commercial GFETs on the market, but I actually also know they're quite expensive. And the quality level in them is not necessarily super great. What I mean by that is you can have an array of GFETs, but not all of them will either function, or not all of them will none of them will function exactly the same. So I think GFET is a nice idea, but I do feel like it kind of is holding things back. Now, I'm biased because at Zimmer Peacock we tend to use printed electrodes like this. Now, the difference between this and GFET is, we can produce thousands of these things, at a sort of low cost. Whereas a GFET is a very kind of, valuable material. You have to handle it. You have to handle it with care. You can't afford to, sort of lose one. And otherwise, when I say lose, you can't lose it. You're gonna have to kind of look after it, etc. So it's something you have to treat with quite care. So it's a bit upsetting when a paper says, well, this is how I made my GFET, because it's like, oh, okay, so you have to go through all that work only to start the science. And I'm going to make an argument in a bit that the real value add is the assays that you designed for the electrodes, not making the electrodes themselves. It's probably worth coming to the academic webinar to see me kind of discuss that in a bit more detail. The other slight problem with the paper I've got as well is that they actually synthesize this reagent. So they've got this reagent called, they call it PDI diacid. So it's an aromatic system that will probably pi stack quite nicely on the graphene. Excuse me. And it's got a couple of carboxylic acids, which they can then kind of couple their aptamer to. The fact that they synthesize it, you can admire them for their science, but again, it's kind of like, the more barriers in order to then go and do the real value add, which is the asset itself. It's a little bit it's a bit of a shame, let's say. Um, Now, I've been aware of this, but the biggest problem I have with GFETs actually is the scientific setup, especially in the R&D facility. So what you're looking at here is that they've got this source and this drain and this gate, and they've got these kind of probes that come in. Now, you have to kind of use these little sort of twiddles, and you bring these kind of things in and you touch the electrode. I'm sure if you've used this stuff, you think, no, it's straightforward. But I would just actually contrast that with one of our systems. Okay, so all right, so I want to make electrical connection with my electrodes. Okay, so what I'm gonna do, I'll take my electrode, I put it in there, I snap that shut. I've made electrical connection. Right, now I want to break electrical connection. All right, I'll take it out again. All right, put it back in. The point is, see, the science has to be fast. If we're playing with the instruments, and it may be interesting and fun, and if you're trained in it, but it's not really adding value. When I'm twisting something and trying to get, and I know how awkward it is. Because I've got colleagues who do this kind of thing, and then they have to kind of get these tiny little drops in there. It's not, you don't have a particularly fast throughput of experimentation, and it ends up actually holding back. I mean, I've got I've got one of my databases where I've done like 200 experiments in the last few months. You can't get that kind of, I think with these probe stations, people are doing a few experiments a day. Whereas we would want to do at least 40 experiments in a day. So I do have a bit of a problem with at the moment the scientific equipment that's actually used to you have to make the GFET, and then B, it's actually really quite painful to actually use the GFET. So this is not a it sounds like a bit of a sort of down on GFETs. I'm sure they're great once it's all scaled up and stuff, but in research you have to fail fast or be successful fast, and when you're tinkering with equipment, it's a bit of a pain. So that's I've always had a bit of a problem with that, with this kind of probe station kind of use of GFETs. That said, I mean, the other thing that I've got a slight problem with is the signals that are reported in this. So what I may make that, I think I might be able to make that point here, that when they go to 1 micromolar, admittedly they get they do delta I over I, so they sort of just do some changing current over I. The first thing is, see, when somebody does delta I over I, what they're sort of doing is they're sort of doing a calibration, because actually the GFETs are so variable. They have to first calibrate the GFET, and then they essentially do the experiment again with the geosmin present. So it tells you about the repeatability of the GFET. So it's very hard to see how this is going to easily, let's say, translate. The other thing is they do talk about their limit. They've used this from sort of 0.01 nanomolar up to about 1 micromolar. This 0.01 nanomolar down here is hovering around about 2%. There's a little bit of an inconsistency later on in the paper, because here they show 10 nanomolar, and that's at 2%. So it's no big criticism. Sort of 10 nanomolar in this paper, in this one, says it actually that the percentage change is about 12.5%, but actually later on it actually says 10%. I'm sorry, 2%. So I'm a little bit concerned that actually the limit of detection, that they may have problems with repeatability, because in the same paper 10 nanomolar is giving a sort of delta I over I of 12.5%, and then later on one of the other figures it seems to be about 2%. So there's a repeatability problem even within the same sort of paper. Now, I don't think there's much evidence in the paper necessarily for specificity or selectivity. So I've got a really strong suspicion that geosmin, there's these other molecules that are also pretty similar to geosmin. I suspect that they would all give a similar signal. It's not a super criticism, but we are allowed to review our papers, and people are certainly welcome to review what I say as well. And there's direct comment, feedback, because you could just comment underneath the videos. Now, the problem I've got, sometimes with these sort of convoluted papers where you have to kind of make everything and then do even before you can start, is this kind of valley of death. So when I kind of came into academia and industry, I was aware of this valley of death, where people talk about we've got this kind of scientific. I should actually just hide this. When I say hide, I'm just going to take myself out of the shot for a second. So you've got something in the lab. They're using something that's very lab orientated, let's say, and it means that really their science stays at TRL 3, technology readiness level number 3. But at Zimmer and Peacock, in order to translate things out of the lab and into the hands of real users, you need to be getting towards technology readiness level number 9. So I'm trying to obviously, and I'm biased because I'm one of the engineers on this, one of the manufacturers, the owner of the company. That we want to use technology in the lab that actually looks like real products, because then we think it's then easier to no, don't think, it's a statement of fact. It's easier to translate the technology out of the lab. So governments are also very interested in this translation or this impact of academic research. And so at Zimmer and Peacock, rather than just doing what governments have historically done, just trying to throw money at this problem, actually we say no, use the same equipment that you're going to do your research on, that you would also do your commercialization on, or your translation out of the lab, and literally close the gap. So what we're saying is, don't use equipment that's otherwise very R&D only centric. Actually use equipment that can be both your educational platform, so you could teach undergraduates, both your research platform and your commercialization platform. So at Zimmer Peacock, I was just kind of saying earlier on, I was a bit worried about the GFET, because you have to make the GFET. I think even in that own paper, they actually had a repeatability problem. You know, here's here's a whole row of electrodes that we snap out and we use. The reason I bring this up is because the value add is actually the assay, not making those electrodes, not making the electronics, not the probe station coming in. The value add is actually designing the assay that will work for geosmin. So we want people and academics to actually focus on where the real value add is. I was talking to a very senior chief scientific officer in California years ago, and he kind of said to me, don't worry about the engineering. We can always do the engineering. Don't worry about the electronics. It's all about the assay. And that's something that's kind of, something that's come through with me over the years now, that actually don't worry about electronics. Don't worry about hardware. Don't keep reinventing the wheel. The real value add actually in a lot of biosensor development is the assay. So work on the assay. So when I say work on the assay, then there's the actual biochemistry itself. How are we going to detect geosmin in this particular case, or chemistry? How are we going to excite that electrode? Now, in the original paper, they were doing what's called IV curves, just current voltage, obviously, not obviously, but I think electrochemistry actually offers up many very, very good ways of excitation. The problem I have a little bit with FET, field effect transistors, is you apply voltage, you get a current, or you sweep voltage, you get a current. Sweeping voltage you get a current, by the way, is, for me, is called cyclic voltammetry, or maybe linear sweep voltammetry. So we do have the equivalent in electrochemistry, but we have then so many other techniques which are actually are increased sensitivity. So there's a whole range of techniques when you can actually come over to electrochemistry. So the value add for me is, what's that assay? What's that method of excitation? And testing with real samples and get a calibration, so you can turn essentially the raw signal into a meaningful number. And I actually do a bit of a demo on that later on as well, I'll do a bit of a demo on this in a bit. So assay development, method file for actually making that assay work, and the calibration routine for getting the data out of that, or getting the information out of that assay. These are the places that we want people to actually concentrate on. Of course, I'm biased. I've got this Sense It All in front of me now, and I'll need to do a bit of a demo on this shortly. Don't worry if your question number 2 about sweat. I will come to that as well. All right, so we're talking about, I'm talking about Sense It All at the moment. If you scan this QR code, this will bring you to the Google Play Store. It'll put an app on your phone. When it says email and password, if you put that email and password, if you put in your email and make a password, that will open an account. You will have then an app on your phone. In fact, I've got my phone here, but you'll see a bit of a demo of this in a minute. You will have an app on your phone called Sense It All. If you've got an iPhone, then you probably live in California. Now, if you've got an iPhone, you can also live in Europe. And if you scan this QR code, then you will also find the equivalent for an iOS phone as well. Scan these QR codes. I might actually scan these QR codes now. So on this app, there's a button. The button is here. If I do that, now this wants to actually scan QR codes. So I'm just going to scan this QR code. It's just opened up amperometry on my app. I just scanned here, so I got amperometry on it now. This is potentiometry, so I'm just going to scan that QR code. Oh, I've got to do it here. I'm so daft. I'm holding it the wrong way. Right, now I've got open circuit potentiometry. Now I will do impedance spectroscopy, so let me just do that. Now I've got impedance spectroscopy. Now let me do linear sweep voltammetry. Bang. Linear sweep voltammetry. Then let me do cyclic voltammetry. Now I've got cyclic voltammetry on my phone. So you can see that I can go through all these different methods. I haven't really mentioned that this is actually a Bluetooth connection with the device that's in front of me, but I just want to do this one, square wave voltammetry. All right, square wave voltammetry is on my phone. Great. So I do have links to this. So I'm sort of suggesting if you're going to do any kind of research on geosmin, I'm super biased, but use electrodes like this. Everything's in place. It's easier to set up and do an experiment. Here's an electrode. Put it in the instrument. Shut or lift this lever up. What it's doing is making an electrical connection when I do that. Done. Now I'm ready to run. I'll do a demo of that in a minute. Use the hardware. The hardware actually, you can go from doing science experiments to actually translating that science experiment into a real product very quickly. And I'll actually give you a demonstration of that shortly as well. So, yeah, you can do amperometry, impedance spectroscopy, cyclic voltammetry, square wave. But those QR codes have already been shown. If I was going to do that geosmin assay, I'd actually do a sort of hybrid between what we did in a previous paper and what that geosmin paper was doing. So this is a paper that I would recommend. I'm an author on it, but it's a simple way of functioning carbon electrodes. So here you use something called pyrene NHS. The fact is, see, pyrene NHS, it's a little pricey. It comes from Sigma, but it's available. You can buy it. So you've already stepped ahead because now you've got electrodes. Then you get pyrene NHS. So now you've got your coupling agent. Then you can add your aptamer. Now I've indicated here as an antibody, but yours would be an aptamer. Now I'm using a reporting molecule in here called ferricyanide. We can discuss why that is, because I got a super suspicion. If I was trying to do this assay, what I would actually be doing is I'd be taking the sample, and I would be taking 50% sample, 50% what I call reagent with ferricyanide in it, putting them together, and then testing that. Because I know then that, well, I've got a source of signal, which is the ferricyanide, and the ferricyanide wants to get to the surface, and when the geosmin is binding, then it should block the surface partially. So we also use something to stop non-specific binding. What I noticed about that paper I thought was quite interesting is I didn't find a lot of evidence that it actually blocked that electrode against non-specific binding. So when they're testing with geosmin, they say it's because it's binding to the aptamer. It could equally be binding straight to the graphene. So they get a signal, but it's a non-specific signal. And anything else that's slightly hydrophobic will also bind to that surface as well. Now the nice thing about this is this particular device. When I say this device, I should talk about this hardware as well. You could, as we functionalize the electrodes, we actually follow the functionalization using cyclic voltammetry. The cyclic voltammetry becomes distorted as we add on layers, which is kind of interesting to see, because I felt the paper was a little bit they've done some characterization of the GFET. So, but we also sort of, let's say, follow as we layer upon materials on top of the electrode, we follow it often by cyclic voltammetry. and then we test. So in this particular case, we'd used differential pulse voltammetry, and as in this case, as the target had bound, then we'd got a change in a signal. So I would suggest that really the way forward is actually to combine things like the aptamer of the geosmin paper, but with the functional and protocols that we actually have in this particular paper. I think trying to do the geosmin paper in a summer with students, unless you've already got GFETs probes, and and even if you've got GFETs in place, I'm sure you already know the trouble of producing them. That probe station means you'll only need to get a few experiments done, so that you need something a bit faster and a bit easier. Now I realize here I wanted to actually I've got you here sweat analysis, but actually I want to do a quick demonstration. So let me just do a quick demonstration. So at the moment, my app wants to do square wave voltammetry. I'm just going to slightly move this out of the way. I could obviously go to amperometry. It's a good old technique used in electrochemistry. If I'm doing binding assays, I actually quite like these days square wave voltammetry rather than differential pulse voltammetry. But what I'll do is I'll go here. Now what I want to do is I want to take a sample. So what I want to do is I will take a sample, which I am doing now, and I will pick up that sample. I will put it on the sensor. I might actually just I'm just going to give this a name, because actually what's going to happen is the data is going to go to the cloud. So let me just say test 24. Just made up the name. I'll put the sample on. I'll do that. I will go to assay. I'll do start measurement. Right. So this is actually now. This is the kind of you've done. I'm sort of arguing that this potentiostat, as well as being able to do all these kind of amperometry, open circuit potential, impedance spectroscopy, linear sweep, cycle voltammetry, square wave voltammetry. We can also, just by using different QR codes, and you can also basically create a QR code for an assay that you're interested in, then, or rather you have developed, suddenly you've gone from R&D to products. Now it's come back with the results here. I'll just change my phone really quick. Yeah, it's come back with the result here of 290 parts per million. So I don't really want to dive into the analyte itself, because the analyte itself is not geosmin. But in fact, it's actually not a bad thing when I think about it in some ways, because we could, we could actually then, you could have done the geosmin assay, and created essentially, once you've got that assay figured out, then actually you can then turn it into a workflow like this where you get a real number. You notice that we didn't show the cycle voltammetry running because we want real people to adopt this technology. But I just want to show you something. It just says upload complete. So I'm just going to share my screen with you for a second. So here goes, because I'm just looking for it. Right. Okay, sweet. Right. I call that test 24. I did tell you that today is the 29th. So this is did it just now. This is the time in London. So it's 9 p.m. And in fact, it was running cycle voltammetry. So here's my cycle voltammetry. Here's my first scan. Here's my second scan. And in fact, this is such a powerful device, because actually I've got my standard electrochemistry all saved in the cloud. But actually on the phone, I was able to show you real numbers. How did I do that? Well, what I did was I'd already saved it. So I told it to look at, this is scan 1, this is scan 2. And I told it to scan 2 to do some pre-processing. And I'd also told it to do signal extraction. I told it to set a voltage window. And I told it what my formula was for turning peak height into ppms. And it basically did all those calculations and sent the result back to my phone. So you can appreciate I ran a cycle voltammetry experiment, but the end user got parts per million, because real people don't want cycle voltammetry, they want parts per million. But it's actually really hard for you to move from lab experiments to units of just concentration. You have to sort of build software and all sorts of stuff. No, actually, the way this device works is it knows what to do because of the QR codes. It tells the device what to do, and the device sends the data up to the cloud. I say the device, the sensor or potentiostat. And in the cloud, then, you can manipulate it by actually programming these. I should turn this off slightly because I realize it's in the way. You can program the tools up in the cloud to actually process the data, and then we send it back to the app, and the end user gets a lovely experience. The end user actually ends up getting these essentially numbers, but you can see here that we've processed it. We found the peak. We turned the peak height into units or concentration and sent that back to the phone. So I just wanted to basically show you how powerful that is. Now, you could change, if you work on your geosmin and you're using this instrument, you can do your lab work and you can have nice experience on easy manufactured electrodes. But then you can also see, oh, okay, well, if I get a functioning assay, now I can actually go and do I can actually develop a real app and a real product. And when I say real product, this is a real product. In fact, flip that out. That's done. Ready to break out one of these and get on with the next let's say measurement. So I did want to show you that, and I think it really resonates. Well, at Zimmer Peacock, we've always had the mindset: let's decrease the barriers between what we do in the lab and what we can then take out of the lab and put in the hands of let's say real people. Somebody wants to do some sweat analysis. So I think with the sweat analysis, you need three things. You need microfluidics, electronics, and sensors. So first of all, let me just bring up the microfluidics. So we do have some microfluidics on our website. If you see a URL, just know that URL is something you can find underneath this video once I've uploaded it. And we do have a video showing you how to construct microfluidics. And you can take one of our sensors. I suggest you very, very strongly, don't go and try and do everything at once. You've got to do one analyte and get it right. Then you can start thinking about other analytes, because people are definitely running, before they've sort of walked, let's say. So here's the microfluidic kit. So you did once potassium, sodium, and chloride. If you're well funded, you want sodium, potassium, chloride, and you want to measure the rate of sweat. If you're well funded, then you can basically engage Zimmer Peacock to do a big program with you. If you're not well funded, or it's an academic kind of effort, then I would say choose one of the analytes, and I would recommend potassium, but sodium is also pretty good for us. And you will need electronics. So in fact, this is the electronics that you need in the left hand here, and they're just putting it onto a developer's board here so that you can actually make communication with those electronics. But what you require is those electronics, and I realize that this electronics these days actually does come with a connector for the sensor as well, but if you follow that link, you will see that as well. You also, and I think I've left it out here, but yeah, you will also need some test solutions as well. So we do have some tests. I have linked to some test solutions here as well. So I did a bit of a landing page specifically for you to try and help guide you in on the relevant technologies. So question number one is about geosmin. I did review the paper. I'm biased. At Zimmer Peacock, we like electrochemical sensors rather than necessarily field effect transistors. There's plenty of people interested in field effect transistors. I think that field effect transistors are actually quite costly. I can understand at scale they should be low cost, but because most people are using them in the R&D setting, they're actually quite expensive. You certainly couldn't afford to kind of damage too many and lose them, whereas with this you can. The other problem I've got then is those probe stations. I'm sure you can overcome that, but why do all that when you can actually have quite an elegant little potentiostat like the one we showed? And then with the sweat analysis, you need microfluidics, electronics, and the sensor. And I've made a special landing page for you, and hopefully you can find the technologies there. Now, what I say is, if it's a commercial organization, then Zimmer Peacock's business model is to actually engage on well-funded paid programs. If it's an academic effort, then we try to help people navigate the website, but we can't get deeply drawn into those programs. If it's not clear on the website how to use the technology, or it's not clear to you, then unfortunately probably um, it's not we can't really then sell that technology to you. But hopefully that website is useful enough and you can follow what we've got there, and you can buy the tech from there. So if you've got any questions on Zimmer Pico, don't forget we do have those webinars, and if you have any questions, don't hesitate to reach out to us. Okay, thanks very much.